we can live longer with the help of oriental medicine. While liberty and democracy are controversial, so to know how can you live longer, we first know why liberty and democracy are controversial. So let me start with liberty and democracy. The liberty problem. When only I have a liberty, world is beautiful. Think traffic jam and the case without traffic jam. As you can see, if all have liberty, there's no liberty. But when only you have liberty, there is liberty. So someone who worships liberty is very selfish guy. Billiard balls problem. When the ball rolls into other ball, they make a turn. This means a change of momentum. And change of momentum is a result of integral of force applying to the ball. This means for Quicksilver to have a lot of turns, he needs continuous force, and force is a different result of potential energy. So for every seconds, the ball loses force, and this loses its liberty as it has a relation with other standing ball, and finally it seems to standing. So, to have liberty, there should be no ball on the table, then the ball can go anywhere you want to go. So liberty is the degree of freedom. Then, what is democracy? Democracy means equality, so everything should move in the same velocity. Let's see billiard ball again. Billiard ball's problem. As the ball has relation with others, the force gets distributed, and finally all balls have the same momentum and last. So democracy means network. And let's see the degree of network, the entanglement entropy. Entanglement entropy. Entanglement entropy. Entanglement entropy is a good tool to measure how much two regions are entangled. And the maximum entropy is limited, which is the value for duality to exist. And I'll show what is entanglement entropy. Consider a quantum system that is divided into A and B, two parts such that the four Hilbert space can be represented as the tensor product of the Hilbert spaces of A and B. Like this. A typical wave function of this system is psi is like this, in which A and B in the state psi are entangled, since psi cannot be written as a simple product of those of A and B. Entanglement entropy is a measure to quantify how much A and B are entangled. Define a reduced density matrix of A by tracing over a B state in psi. Then entanglement entropy is defined as this. From the definition, an obvious corollary is SA is 0, low weighted of pure state. Psi can be written as a simple product. Indeed, for any pure state, we can always write it as psi is like this. By Schmidt's decomposition of psi into some complete set of A and B, it follows that SA is SB. For AB composite system in a mixed state, in general we have SA is not SB. In such a case, entanglement entropy typically contains classical statistical correlation of the mixed state in addition to quantum correlations. Here are some examples. A two-spin system, we can have a state like this that is not entangled. However, the state psi is cosine theta down spin of spin plus sine theta up spin down spin is entangled. For this state, the reduced density matrix for A is like this. Shows entanglement entropy is SA is my cosine square theta log cosine square theta minus sine square theta multiplied by log sine square theta. We see SA has period of pi over 2. Zeta and minima are SA is 0, which zeta is n pi over 2, and maxima are SA is log 2 when zeta is like this, where n is integer, and maxima the state psi is 1 per root 2, downspin upspin plus upspin downspin is most entangled. We list some important properties of entanglement entropy as follows. Suppose ABC are three parts of the system without any interaction between any two of them. We have subadditivity and strong subadditivity. Entanglement entropy plays an important role in quantum information and quantum computation as it provides quantitative measure of quantum correlations that are not present classically. Consider system AB. If Hamiltonian is HA plus HB, then the ground state is unentangled. Moreover, starting with a general unentangled state, the system will remain unentangled. If we add coupling between A and B, H is HA plus HB plus HAB, then the ground state is generally unentangled. Suddenly, starting with initial unentangled state, entanglement will be generated during time evolution. In all realistic condensed matter systems and quantum field theories, HAB is a local Heisenberg model. And pi over 4 quantum field theory, Lagrangian is like this. Locality implies, as shown in the picture below, that the interaction only happens near the interface of A and B. So HAB only involves degrees of freedom near the A and B. This has important implications. This is the locality of interaction. One finds in general in the ground state for a local Hamiltonian entanglement entropy given by like this, where epsilon is the lattice spacing for CM system or short distance cutoff for quantum field theories which characterize the geometric width of interface. This formula shows that entanglement entropy between A and B is dominated by short-range entanglement near the A, where HAB is supported, while 16 appears to be universal. Number is not, depending on short-distance physics of large-range entanglement, and can provide important characterization of a system, characterized topological on the 2 plus 1 dimension. In typical gapped systems, ground state contains only short-range correlation. In topological order systems, ground state contains long-range correlation, now accessible via standard observables such as correlation functions of local operations. The entanglement entropy for such a system is like this, where gamma is not zero, is topological order, a constant independent of shape and size of A. Characterize the number of degree of freedom of a quantum field theory for a 1 plus 1 dimensional quantum